Bismillahirrahmanirrahim. Assalamualaikum. So still we are going to discuss membrane separation. So if you recall, for last 2 weeks we have discussed we started with the membrane separations 2 weeks back, and in the first week we discussed related to membrane separation, their basic terminologies, and some basic stuff application in the industries related to membrane separation. And then in the last week we have discussed about membrane material, their synthesis, and the various modules, how membranes are actually placed in industries, or how membranes are arranged, because there you need large surface area, you need large number of membranes, so how you have to arrange them. So this we have discussed last week, and at the end of that lecture we also just touched how you can synthesize membrane. There were various methods, although we didn't go in detail, but we have just touched them. That there are various methods that are used to synthesize membrane on large scale. By this week, actually this week and next week we have to discuss some specific membrane application like reverse osmosis, gas separation, and electrodialysis or pervaporation. But before that, in this today's lecture, we have to just look at few more terminologies related to membrane that will be helpful in the topics which we will discuss in next few lectures as well. There is one general equation which is applied for membrane systems. Let's talk about this. Initially we have to start this lecture, and we will look at one general equation which is used commonly for membrane system, especially those systems which involve liquids. And before this equation, I will just introduce you with a few more terminologies. Few are the common things which you know from earlier, like FSC classes even, but just to refresh your knowledge, we will discuss few terms like diffusion, osmosis, because we are discussing these terminologies for long. Then we will quickly look at the mass transfer through membrane, some general stuff related to mass transfer, and by next lecture we will start with specific application. So here we have diffusion versus osmosis. So diffusion, so here is diffusion versus osmosis. So diffusion is actually movement of solute molecules from where from high concentration to low concentration. So when solute molecules move from high concentration to low concentration, we call it diffusion. So for example, one example given here, like if you have one solvent which is in large quantity, large amount inside a beaker, and then you add some solute molecules. So you just add them to a specific location, but you know that after some time they will be distributed inside whole solvent. Why they get distributed inside whole solvent? Because at the place where you add them, their concentration will be high, they will be available in the large amount, but in the surrounding there is no solute, so they will just start moving from this high concentration to the other concentration where no solute is available. So this phenomena is named as diffusion. Solute and solvent, you know that solvent is something which is present in the large amount, and usually when you look at the system, for example, you have water, and inside that you add some salt or some sugars crystal. So sugar or salt are behaving as a solute. While when you look at the osmosis, so osmosis is somehow opposite to this, or that's first of all movement of the solvent molecule. So in diffusion you look that's solute molecules, but osmosis describes solvent molecules movement. So when solvent molecules move from low to high solute concentration, they move from place where solute concentration is low to the place where solute concentration is high, but here major movement is solvent. and this movement, by the way, takes place through some semi permeable membrane. For example, you know this example that like you have one beaker. Inside this you can see that there is one semi permeable membrane, and semi permeable mean which allows few particle to pass through or few component to pass through, and other it didn't allow. For example, we just consider that this membrane allow only liquid to pass through, solvent to pass through, while solute or these solid particles cannot pass through this membrane. So if you just fill two sides of this beaker, one side contain large amount of solute, like here you can see for example, just it is shown to you. From this you can see that solute molecules are higher on one side as compared to other side, and overall there is level, liquid is leveled on both sides, it's equal. But what happens after some time, as this is semi permeable membrane which allows liquid to pass through, and here phenomena of osmosis takes place. It is the natural tendency of the solvents to move from low concentration of solute to the high concentration of solute. So what will happen if you keep this system for some time, you will see that naturally this liquid or solvent has traveled from this left side to the right side. It keep on moving, although through this membrane this liquid can move on both sides, but overall if you look at the net amount, so overall this solvent will move in higher amount from left side to the right side. So after some time you will see that when this system reach to the equilibrium, so overall solvent amount has reduced on the left side and it has increased on the right side. For example, for this you can consider, if maybe you are confused, just consider for example here this was half liter water, or we can say okay 1 liter water on both side of membrane. There was 1 liter, and in this 1 liter, suppose on this side you have only 5 gram of some solute, and on the other end you have 50 gram of the solute. So this is 50 gram per liter and this is 5 gram per liter. So on which side concentration is higher? Definitely on right side concentration is higher. So water will start moving from this left to right, and when you see that water will move from left to right, as we said this is semi permeable membrane which allows only water to pass through. So what will happen, on the left side amount of water will start decreasing while salt will remain same. For example, we just consider that after 1 hour or after few minutes, for example, just we just say that 0.2 liter of water has moved to the other side. So here how much amount will be left? It is 5 over 0.8 liter. On the other end, what it will be like, it will be now 50 gram, that's salt is almost constant here, and the liquid will be like, now it was initially 1 liter, so now it will be 1.2 liter. So with this you can see that overall concentration will start decreasing. Here it was 50 gram per liter, but now when you are dividing it by 50 divided by 1/2, so its amount is at least reduced from 50, but on this side it has increased. So this phenomena will continue until your concentration is equal on both sides. The liquid, although here this will get balanced, or this will reach to equilibrium when small amount of liquid will be left on left side, and there will be high amount of liquid on right side. Then this will reach to the equilibrium. At that stage actually liquid transfer or this solvent transfer from left to right or right to the left will be equal and it will stay balanced. So this phenomena is called osmosis. Later on we have to discuss something reverse osmosis, so we will look at that later, but here at least for this lecture you should be aware that there is a difference between diffusion and osmosis. And what is osmosis? Osmosis is actually movement of solvent molecules from low concentration of the salts or solute to the high concentration of solute. So here we are going to actually discuss something called osmotic pressure. So before osmotic pressure, you should be aware about osmosis. Now you are aware about osmosis. What osmosis is? That movement of solvent molecule through some semi-permeable membrane. So in this example, just look at this, that you have like one U tube or something like test tube. So in this, so okay, in this tube you have one semi-permeable membrane which is placed at the center. So on the both ends of this or both sides of this semi-permeable membrane, you fill pure water. This is water which may contain some other impurity, but this is same water. So overall, what you will observe, suppose you fill this water on both ends and its level is same. So based on the discussion of the last slide, what do you think? Will water move from one side to other side? Yes, this is semi-permeable membrane. We just consider here, for example, that this membrane only allows water to pass through. So what will happen? Water will transfer from left to right or right to the left, but this amount will be same. So overall level of the water will stay same or will be kept same. But what happens if you just add sugars on the one side? So you just add some amount, for example 1-2 gram of the sugar on the one side, only one side of the tube. So now what do you think? On this side, left end of this tube, amount of salt has increased. So overall concentration on this side, concentration of the solute will be higher on this left end, left leg. This will be higher, while on right side, that's mean just simple water, you didn't add any sugar. Now what do you think? What will happen? Phenomena of osmosis starts. Yes, definitely from here, from right side, water will start traveling to left side. Although we know that through this membrane water can move on both ends, but as the salts or this sugar is added on the left side, so major or more or heavier quantity of water will travel from right side to the left side. And this transfer will continue or will keep on going unless both sides reach to the equilibrium, as I have told you in the last slide, that this continues until concentration or like overall this amount of salts per amount of this solvent becomes constant, or become not constant, sorry, become equal to the both ends. So this water will start moving from left to the right. So overall what you see here, what you can observe, that water amount will start decreasing on the left end and on the right end, and it will start increasing on the right side. It will start decreasing on the right side and will start increasing on the left side. So if we do not want this water to travel from this this side where there is a pure water to the other side where there are salts or sugar is added, so what you can do, here you can apply some external pressure. Actually, if we apply external pressure on this side only, so what will happen? Water will be pushed to the other side, and this will be balanced. Suppose if you were here on this end, you added the sugar and you saw that water has started traveling from this right side to the left side, but I do not want this water to move on this side, I do not want this osmosis to take place. So what I can do, I can just apply pressure. Now this pressure should be how much? This pressure, external pressure, applied pressure, should be equal to osmotic pressure. Maybe some of you will be thinking like, here there is already atmospheric pressure, so atmospheric pressure is same on both ends, and in that case that cannot stop this water from traveling from this end to the other end where there is more salt or there is high amount of the solute. So this can be avoided if we apply some external pressure higher than this atmospheric pressure. So that pressure should be equal to the osmotic pressure. Let's look at few more example and then we will define osmotic pressure. But up to here, now you know that if we have pure water, there is equal transfer of maybe water molecule and level didn't change. But if we add salt or sugar on one end, so what will happen, water will start moving from other end to the this end where you have added sugar. So due to this level change on the both side, amount of liquid change on the both sides, across both side of this semi permeable membrane. And if you want to keep the level same, you do not want this liquid to travel to the other end, so what you have to do, you have to apply some external pressure. So in this example you can see that you have filled again on one side there is pure solvent and other side there is a solution that contains some solute. So what will happen if you just allow, or if you just place this system on the atmospheric pressure, you know that this solvent will move from this side, major amount will or large amount will move from this side of pure solvent to the solution side. This phenomena is called osmosis, and this takes place through some semi permeable membrane, and this membrane didn't allow any salt to pass through other side. After some time, when it reached to the equilibrium, what you will see that the level on one side has increased as compared to other. So here you can see this difference of the height. So overall you can look at this, that this is main difference in the height, and you can use this stuff to calculate the pressure difference between two ends, or which you will call it as osmotic pressure. Similarly, here you can see that in this example again, we have filled this tube with the pure water and solution. In this you have water with the glucose. So there is semi permeable membrane, and through this membrane, as he has shown and I have told you, that through this membrane liquid, this water can flow to the both sides. But what do you think, on which side water will move in large amount? Definitely on the side where there are more salts or glucose is present. So if you allow it to reach to the equilibrium, after equilibrium you see that there is a difference in the height. So again, now in this system, if we do not allow this water, or if you do not want this water to travel to the other side through this natural phenomena of osmosis, what you can do, you can apply pressure on the other end, and this pressure should be equal to actually osmotic pressure. So when you will apply this external pressure equal to osmotic pressure, as he has shown it with the symbol pi, so that's will transfer this liquid. When you will apply this high pressure, so it will just push liquid from this end to the other end through this membrane, and with this you will get both are leveled, though both side liquid is now leveled. So if we want to avoid this natural phenomena of osmosis, what we can do, we can apply pressure so that liquid didn't travel to the other end. So from here you can define osmotic pressure, that defined as the pressure that must be applied to the solution side. So what do you see here, where we are applying the pressure, we are applying pressure on solution side. Either in this example you have seen, or the last slide here you can see where did we apply the pressure, where we have to apply the external pressure, that's equal to osmotic pressure, we have to apply on solution side, not on the pure liquid side. Solution side is the side where there is solvent as well as some amount of solute towards the their pure liquid was moving, so that side. So osmotic pressure is the pressure that is applied to the solution side to stop fluid movement, or we should say that pure solvent movement by osmosis, when a semi permeable membrane separates a solution from pure solvent, or for example here water. It is not necessary always to have water, but commonly we have to apply this system, or commonly you see the examples of water. Due to this he has mentioned the water, and here this fluid mean water then. So now you know that osmotic pressure is actually pressure which is applied externally just to avoid the movement of fluid from which you know from low concentration of the solvent to high concentration, and that phenomena is solvent, to avoid the movement of fluids by osmosis through a semi permeable membrane. So osmotic pressure is actually physical quantity, and which depends mainly on concentration and temperature of the solution. So if you look at various texts, you will see that even ideal gas equation is used for calculation of this osmotic pressure. So you have with that PV is equal to nRT. So you know that we have seen this is pressure, so that pressure can be calculated by using this equation nRT over V, and N over V is actually molarity. This is number of moles of solute per unit volume of the solution. So this is V is the volume of solution and the number of moles, so it is mRT, M capital, that is used for molarity, and molarity is number of moles of solute per unit volume of the solution. So this P, that is also equal to pi, just to differentiate it from the pressure, because here in the membrane system we have also other pressure, so just to differentiate it we just represent it as with pi. So pi is equal to mRT. That's from here you can see that this depends on concentration. Molarity actually involves this unit of concentration, and this depends on the temperature. So from here you can calculate osmotic pressure. So where we have to use, actually next we are going to look at one general equation for membrane systems, where you have to use this terminology osmotic pressure. So now you should be aware about this osmotic pressure, osmosis, what is diffusion. So these are the terminologies which we have discussed so far. If we are designing any system, or we are looking at some membrane separation system, so maybe you can think that we should have only one equation that can give you the information about permeate, amount of permeate, how much permeate will be, you will collect, how much will be retentate, or how much separation takes place. Maybe such equation is not possible to get, like there is not only one equation which can provide you all the information for permeation rate, solute, rejection mean anything which is like here retentate, for a real separation. So you don't have any one equation or a set of equation which can predict that directly, that how much will be permeate and solute rejection, but somehow there is one equation that is used to calculate some flux, or let's look at that. But before that, why it is difficult, why it is not possible, the reason behind that is like you know that various system will have various properties. System mean both membrane as well as the solute, or the liquids which you are passing through this solvent, which are passing through the membrane. For example, in the last week you have discussed that there are various membrane materials which can be used, and suppose we are using some specific membrane for some specific application, for example for gas separation, that gives good result, but because that has some good interaction with those gas molecule which are passing through. But maybe for the liquid, that's not good choice, that's not good one, because you have hundreds of various system, various chemicals which need to be separated using membrane. So to look for interaction of all membranes, our membrane material with your solute, they have different interaction. So due to this, you can't predict all this stuff by using only one or set of equation, but people have developed one equation that relates some of the factors which are important during this membrane separation process, and that relate, or that helps us to determine the membrane permeation rate, or how much will be the flux through the membrane for a pressure driven processes. This is not natural phenomena in which just naturally, like the system which you have just seen in few slides back. So there was natural phenomena, and that was taking place on just atmospheric pressure. But if we have to apply high pressure, and through those system we look at the permeation rate, so there is one equation that can predict somehow the amount of permeation, and this is derived through various steps. We are not going through that, or that's not also considered as a part of your syllabus. By the way, this lecture I have brought it through various resources, through some membrane books, through some other books. So maybe this stuff which I have discussed so far you will not find in your textbook, but last few slides they are that's that stuff is available in your book. So just go through these this lecture and these slides, and just google it few terminologies if they are not clear, but otherwise you will not find in your textbook. So this J is equal to del P minus del pi divided by Rm plus Rc into mu. So let's look at these terms. What does all these terms in this equation mean? J, as we said that this indicates membrane permeation rate, so J is called actually membrane flux. And that flux mean, what does this membrane flux mean? Volumetric flow rate of something per unit area through the membrane. Volumetric flow rate of, suppose any liquid is passing, so it will be like volumetric flow rate of that solvent per unit area. So otherwise if some gas is passing, so it will be volumetric flow rate of that gas per unit area. Mean any species that is passing through the membrane, that's called permeate. So it's this will give us the flux of our flux of our permeation rate of that permeate stuff. Delta P is the pressure difference applied across the membrane, or you also name it like transmembrane pressure. Transmembrane, suppose this is our membrane and that is placed in some module, like for example this is closed system in which here is a membrane. So just we are just considering one membrane here, and if you see that through this membrane here feed is entering, and through this feed, then this feed some stuff move to the other side as a permeate, and other some will leave from here as a like retentate. So if we have a pressure, definitely there will be some pressure on this side of the membrane and other will be pressure on the other side. So if suppose we say P1 and P2, so that's the difference across the membrane. So transmembrane pressure, if you just see this terminology anywhere, so it's mean the difference in the pressure on both sides of the membrane, that's called transmembrane pressure. So delta pi, that's called the osmotic pressure difference across the membrane. So there will be osmotic pressure, as I have told you in the last slide, that this osmotic pressure you can calculate just by using simple equation of the ideal gas law. So that's there will be some solute concentration on this side as well as solute concentration on the other side, and if you know the temperature on both sides, so you can easily calculate pi, osmotic pressure on both ends, and definitely then you can calculate difference in those osmotic pressures. So this Rm is called resistance of the membrane for that solute to solvent to pass through. So or any solute which is passing through the membrane, it depends on its application, any gas or any liquid. So how much membrane is resisting to this. So hopefully we will discuss this terminology in next lecture somehow about membrane resistance. So this Rc is the resistance of the layer deposited on the membrane surface, for example filter cake or gel. So if something is deposited on the membrane, suppose some liquid want to pass through this membrane, so if you just consider there is one pure completely clean membrane and some liquid is want to pass through this, so definitely this membrane will provide some resistance to that liquid to pass through. But if this membrane you are using it for a long time, so what will happen, that some impurities are deposited on its surface. So for example, you were removing some salts from water, and after some time clean water was passing through this membrane and salts are retained on its surface, that's as a retentate. So definitely you will be removing salts from this system, you will not allow accumulation, but some amount is accumulated on the surface of membrane, and that can form a like cake, that's he is calling as a filter cake. For example, you go for filtration and on the surface of filter some cake is deposited, that's filter cake. So similar will happen because membrane is one type of filter actually. So here some cake is deposited or some gel like deposition of those chemical takes place. So they will also provide some resistance to that liquid now to pass through, because initially there was only the single layer of the membrane, but now on the surface of membrane now you have deposited some gel or the filter, so its resistance is also counted. So you can just link it with somehow like resistance of heat transfer. As you know that when heat transfer is taking place through this some surface, you know that there will be resistance of conductivity through this membrane for any this heat to pass through. But if some salt layer is deposited on its surface, so what happen, they also provide some resistance. So same is happening here actually. So their resistance is for heat transfer, and in this case here resistance is actually for this mass transfer. That's the flow of some solvent or some gas through that membrane. So this is one general equation which predict mostly the parameters which are which affect the permeation rate or the flux. Although in this equation we can't see somehow something about the interaction of those molecules or those solvent or gases with the membrane material, but this gives us information with respect to the pressures and also resistance which are which will affect this flux when this separation takes place. Or somehow these resistances are actually including that interaction, because if this membrane maybe that will provide resistance to all of solvent, this will be different. So this is somehow accommodating that factor, and pressure across the membrane is accommodating the factor for this flux. So for example, this was if you have some liquid, like there was a water and we have some salts inside this, this will be valid. But for example, this whole equation will be actually valid. You have to consider each and every terminology. And mu, by the way, this is for what? Viscosity. So that's for viscosity of this system. Overall this will be like your solvent which is passing through this system. So for example, if your membrane exposed to only pure water, so for example we say that water is only passing, pure solvent is only water, and then what will be your equation, or how this equation will change? For example, if you have only pure water, so what do you think? For example, we consider a membrane system in which there is a pure water, and you place just semi-permeable membrane. As for example, you have seen in one of the example where we started that there were a tube, and on there was semi-permeable membrane in between, and there was pure solvent water on the both ends. So in this case, there will be any osmotic pressure or change in the osmotic pressure, this difference in the osmotic pressure? No. For example, this is pure water, so it didn't contain any salt. So when there are no salts, so n number of moles of solute will be 0. So based on that, your if even salts are present and they are equal on both ends or both sides, but here as we are considering pure solvent, so we just consider there are no solvent, pure no solute, no salt here. So in that case, your pi, as I told you, that is equal to n over v RT. So this n over v RT, n is 0 for in this case pure solvent, because you are using, there is no solute, so pi will be 0 on, and there will be change in pi, that will be 0. So this term will be omitted. But definitely there we just considered that there is water and there is a difference in the pressure, so that will be available there, delta P. Rm, resistance of the membrane for this solvent. So definitely this solvent want to pass, for example water, so this membrane will provide some resistance, so this terminology will be considered. What about RC, or filter cake or gel? Because you are passing pure solvent through this system, so there will be no gel formation, no filter cake, so this terminology will also be omitted. So overall your equation in this case will be equal to J is equal to delta P over Rm into mu. Okay, so this will be equation when you will have only pure solvent. So here more important will be like resistance of membrane for that solvent, as well as pressure difference between these two ends, and at given temperature pressure condition your viscosity of the system will affect this J or flux. So overall from here you can see that in this was for pure solvent, but just consider it for like solutes are present in your system. So this equation showed that transmembrane pressure must exceed the osmotic pressure for flow to occur. What does this mean? If you look at this equation, for example, if we want the flux, if we want the permeate rate, if we want some amount of flux, so in order to get that amount, what you have to do, you see, if you look at these parameter of this equation, so definitely if we have to get this J, this delta P should be higher than this delta pi, that osmotic pressure difference. Pressure difference across the membrane should be higher than this, otherwise this phenomena of permeation will not take place and you will not get any permeate. So overall this pressure difference across the membrane should be high than this osmotic pressure. If we know the osmotic pressure and the pressure on the both sides of membrane, so then we can apply pressure on the one side. So with the help of this, more flux will take place and amount of these permeate will be higher. So from here you can get the idea that if pressure across the membrane, pressure difference across the membrane is higher, more flux will take place. More component, for example solvent, will pass through and you will get more amount of that material. Then overall you can see that there is a resistance of membrane. We can control it by using or by choosing different materials. For example, if you choose such material which has good affinity for one of the solvent which has to pass through this, so this resistance will be less. For example, for heat transfer, what do? You select the material which has high thermal conductivity. So here we will select such material of the membrane which has which allows large amount of that one of the component to pass through. At the end of this lecture I will tell you about this selection of the material, how you have to do or on which factor it depends, but that will allow us suppose for example its amount its value, if its value is low, Rm, its resistance is low, so in that case definitely flux will be higher, its resistance should be low. And if you look at this RC now, before I go to RC, this mu, viscosity. So if viscosity is lower, definitely high flux, and if viscosity is higher, large value, so flux will be low, because that's another resistance for the liquid or for solvent to pass through some system. So viscosity of this, if it's viscosity, for example if you want water to pass through some membrane, so that can pass easily because it is less viscous. For example, membrane has good interaction with that, but at the same time if you have honey or something which is more viscous like honey, so in that case it is difficult, you have to apply maybe high pressure to pass through this membrane, so that becomes difficult, so that should have low viscosity. Now look at RC, this cake factor, or you can say due to filter cake or gel formation. So this resistance is due to formation of filter cake or formation of gel. When the concentration of macromolecules on the membrane surface exceed their solubility, this gives rise to a precipitation. Why this takes place, why this filter cake is formed? Actually, macromolecule, large molecule, for example we consider these sugar molecules which are present inside water, or any other molecule which are present in water as impurity, or you can consider as a solute. So if the concentration of those molecules on membrane surface exceed their solubility, because they were initially soluble in the water, but as water is just leaving from this system, when you are filtering this water, so this solute concentration will start rising, and then this solute concentration is higher. Now they will start accumulating on the surface of membrane and they make like filter cake. Next phenomenon, due to materials in the process feed that adsorb on the membrane surface, producing an additional barrier to the solvent. Sometimes it is not necessary that they get salt amount precipitates out from the solvent. Sometimes actually solute molecule which are present inside the system along with the solvent, they can adsorb. Maybe membrane surface has such affinity for them, that they will adsorb on the surface. Now when they are adsorb on the surface, they will be definitely providing extra resistance for the solvent to pass through this membrane. So due to this phenomenon takes place. So what do you think, in order to avoid this resistance, if we want to avoid it or if we want to keep it smallest, what you should have actually is RC value, as it is in denominator of the equation, so you know that its value will be lowest, smallest one. So what we can do, we can clean the surface of the membrane after some time. So maybe if some of you have membrane system at home for drinking water purpose, so you have to clean the membrane for after some time. Membrane cleaning is necessary. Why we go for membrane cleaning? Actually to remove all this stuff which is accumulated on the surface of membrane, because that resist, although membrane resist our liquid to pass through, but at the same time they are also providing some extra resistance which we have to stop. The separation of the solute by the membrane give rise to increased concentration of that solute at the membrane surface. When this separation takes place, later we will look at this, although up to here we have seen that through osmosis actually liquid will pass from side of low solute to the high solute, but actually when you are going for reverse osmosis and all these other main membrane phenomena, you push the water, and with the help of that pressure actually we pass water opposite to the osmosis system. So in that case actually when water leaves from somewhere, so salt or solute concentration start increasing on the membrane surface. So when this start increasing on the membrane surface, that phenomena is named as actually concentration polarization. When salts are there, they are deposit on the surface and their concentration rises, so that's called concentration polarization, this phenomena. Which phenomena? The phenomena in which there is increased concentration of the solute on the membrane surface, that's named as concentration polarization. So when concentration polarization takes place, actually it delays or it reduces the amount of permeate through the membrane. So we have to clean the membrane, so more solvent can pass through the membrane and you can get good separation or a large amount of permeate. So this was about this journal equation. From here you can see that if you have to increase, just now look at this equation. This equation have accommodated lot of stuff. If for example you are using or you are selecting the membrane system, so you want to increase the permeate, because in this case, by the way, in this example which we have discussed here, permeate is your desired product. So most of the time permeate is your desired product. Sometimes retentate is even desired product, but in that case definitely, even if you are separating something and you want to keep retentate as your desired product, so you will want that most of the stuff which you want to get rid of should pass through the membrane. So in any case, if you have to increase its flux, so your pressure across the membrane, pressure difference across the membrane should be higher. As it will be higher, so more flux will take place, and at least this should be higher than the osmotic pressure. Then you are selecting the material of membrane, so that material should provide or should give less resistance to the solvent to pass through. As well, you should avoid the deposition of cake or this gel formation on the membrane surface. So how you can avoid? You have to clean it with the passage of time, because it will start resisting. So from these parameter, as well at the end there was last parameter about viscosity. So your liquid should be less viscous which you want to pass through this membrane. So in the case of this liquid, how you can reduce the viscosity? Maybe by increasing the temperature. Although with this we will have some other problem in the membrane, maybe we will discuss later in next lectures, but at least with that you can reduce the viscosity, and due to reduction in viscosity this flux will increase. So these are the general parameters which you should keep in mind when you are designing a membrane system, that pressure difference, selection of membrane material, resistance due to cake formation, and viscosity of the membrane are somehow important parameter which can give you a bit clear idea about some system. Although again here if you design some system, so because you are not accommodating all the parameter of interactions, and that, so you can see some of maybe you were expecting more flux but you are getting less flux, so there can be some other problem inside that, but this is somehow close to the real systems. So let's look at the mass transfer through membrane. Suppose you have to apply membranes, so membrane surfaces which are applied for various applications, so they are based on actually laboratory data. For example, you are going to use membrane for any separation. So first of all, you have to run some preliminary experiment on lab scale, so you can get the idea about all the stuff which we have discussed so far in last few slides. So so that membrane should perform well as per your expectation, or it should give good separation as well as good flux, and should work for longer time. So because both the driving force and permeability, permeance through the membrane, you know that permeance was permeability over thickness of the membrane. They depend on the mechanism of transport. It is important to understand the nature of transport through the membrane when you are going to select the separation process. What does this point mean? Actually, you have discussed various membrane types last week. So we saw that there were porous membrane, there was dense membrane, and among porous membrane there were different types. So among all that stuff, actually if we are going to design some membrane system, so that depends on the mechanism of transport, how transport of some liquid or some gas takes place through the membrane. So we should be aware about that, and when you are going to select the system, and this transport actually is the mass transfer through the membrane. So as you know that membrane can be microporous, or dense membrane, which you have discussed that some are microporous. Macroporous membrane will have actually pore size greater than the microporous. Among microporous, you have seen three type of membrane. There were micro, ultra, and nanofiltration membrane. So if pore size are higher than their range, so they are considered among macroporous membrane. So usually these macroporous membrane, they are used as a sport. If you remember, I have told you that across the membrane pressure is high, so in order to sustain that pressure, we discussed that usually dense membrane or microporous membrane, that's just small layer, but that is supported with some other support which are usually microporous membrane. They are not used, like they didn't give any separation, they are just used for separation or supporting the membrane thin layer, because if thin membrane of dense or microporous membrane is exposed to high pressure difference, this will rupture. In order to avoid that or give a strength to that membrane, we go for macroporous membrane, and macroporous membrane are just used as a support. They are not active layer, they are not being used for separation purpose, they are just being used for support. This we have discussed in detail in last week, so if you have any confusion, just go back to those slides of membrane types, and there you can see this stuff. So why we apply, by the way, greater pressure difference, this you have seen in last slide. To achieve high flux, we apply the greater pressure difference across the membrane. So when you want to apply greater pressure difference, so in order to avoid the rupture of membrane, what you have to do, you have to just support your membrane active layer on some large pore size membrane. So that will be just being used as a support, that is not like active layer. It will just definitely allow anything to pass through this which have been separated from active layer. So there are two types of majorly membranes, as we know that this is microporous and dense membrane. So we have to look at mass transfer through these membrane, because I am telling you these macroporous are membrane with high pore size, so that's not being used for separation, that is being used only as a support. So here we will discuss mass transfer through microporous or dense membrane. So microporous, if you remember from last week, so microporous or porous is the same terminology, and dense or non-porous is the same terminology. So here let's look at these porous or microporous membrane. So if you look at this, here we are shown with the different system. By the way, this is from your textbook, half a page you can read through this. I will just explain it here. So overall there are 4 systems shown to you here. They are actually porous as well as microporous, and some dense membrane system is shown here, and we have to discuss based on this. So if you look at this first, through first membrane A system, you see there are very large pores between the membrane structure, inside membrane structure, very large pore, and they allow anything to pass through. So however, overall in this example, you can see that anything can pass through this membrane pores. And by the way, this membrane surface does not interaction with any of these, so it will allow everything to pass through, and this we call that bulk flow will take place through these pores. When bulk flow is taking place, so bulk flow is actually the flow of everything on the large volume, anything which is coming inside that system, that will pass through these pores, and they are actually macroporous membranes. So these membrane, no separation will take place because they allow anything to pass through, there is no separation. So next, for example, in B case, you can see, so in A case there is no separation, so these are not membrane which we are looking for. We are looking for something where some separation can take place. So in next case, you can see that this is diffusion through pores. So here diffusion is taking place through pores. Some of these things are passing through the membrane. So overall in this, you can see that pore size are still large, and anything can pass through, but membrane material has interaction, or this is affinity, this has potential for some of the component which it allows to pass through, other they can be retained on the surface of membrane. So through these membranes somehow separation can take place. And these are again microporous membrane. In microporous membrane, you have seen that there were micro, ultra, and nano filtration membrane, and some of ultra filtration membrane, they have very large pore size. So this can be example of that, but that is used for separation mainly based on pore size as well as somehow with interaction with the membrane. Then there is this porous membrane which has very small pore size. So based on this membrane here, actually restricted diffusion through the pores takes place. Restricted means it allows only some of the molecule which has lower size or lower pores dia as compared to this pore size, they will pass through this, but other with higher pore size can't pass through this. So here also good separation will take place. So here molecules larger than the pores are prevented from diffusing through the membrane. Definitely if they are larger, they can't pass through this membrane, and they will be retained on its surface, either it retentate, while other which pass through this membrane will leave as a permeate. So this special case is highly desirable, because definitely when you are looking for microporous membrane, you want the separation based on pore size, which we have discussed in last week, that these are membrane which are making separation based on pore size or pore diameter, and this is referred as size exclusion or the sieving. Size exclusion means exclude some size which is larger than this pore size, and include or to allow pass through some molecule which are smaller in diameter. So this is called also sieving. Sieving, you know that sieving is a phenomenon in which you just separate something based on pore size, something which has large diameter from that sieve pores, so that will not pass through, but if diameter is less, so it will pass through the membrane. And the last D here, you can see that solution diffusion membrane through dense membrane. I told you that usually they don't have any pores, or if pores, they will be of very small size, but through these membrane, actually how separation takes place, diffusion through the membrane will take place, and we have discussed this phenomena in last lecture in last week. So through this diffusion, actually separation takes place. Now this membrane has good diffusion, or it allows some of the component to pass through and others will not pass through this membrane, and separation will take place. But this is not on pore size, this is pure based on the affinity of membrane for some component, and its resistance towards some components or some of the molecules. This was through porous membrane, but if we look at this through non-porous membrane, the D case which we have discussed. By the way, in your textbook he has discussed after this various phenomena of this interaction of, as I told you in this case B case, that interaction of these molecules with the membrane surface, even they are passing through the pores, then diffusion of the liquid, diffusion of the gas through these pores. So he has discussed those topics in detail. That's not part of your syllabus, so don't go through all those equations. Due to this I have just skipped all that stuff which we don't need, or they are not part of our syllabus, and we don't have any also the time to go through all that stuff, those derivations. So this just you should know that how mass transfer takes place through the membranes, just general phenomena which I have explained here. And through non-porous membrane, again same, mass transfer through non-porous membrane or dense membrane. We also look at them as solid membranes because they don't have, most of the time they don't have pores. So here predominant phenomena in membrane separation or this phenomena is commonly involved in reverse osmosis, gas permeation or pervaporation. When we will look at these in next lecture, so you will see that most of the time these separation or this membrane application involve actually non-porous membrane. So all both liquid as well as vapors can pass through those membrane, and separation takes place. As indicated in figure 14.6d part in the last slide, I have shown you that this is through non-porous membrane. Gas or liquid species actually absorb on the feed side of the membrane and diffuse through the membrane, and then desorb on permeate side. If you look at this here, you can see this is the feed side, by the way. From here this gas is entering, and or even if you can consider it as a liquid or gas, anything. So on the feed side they get dissolved or they get diffused through this side, they pass through the membrane and leave on the permeate side. So anything which will not pass through, that will be leaving as a retentate from here. So same point is explained here. So here liquid by the way, here when diffusion through the membrane takes place, you know that diffusions of gases as well as we said that they are applied for gas as well as liquid system. So diffusion can takes place for both gases and the liquids. So liquid diffusivities are several orders of the magnitude less than gas diffusivity. So if you look at some component, for example its diffusivity that exists in the form of liquid or that exists in the form of vapor, some same component, so its diffusivity when it exists in the gas phase, that will be higher as compared to this diffusivity inside when it exists in the form of liquids. So suppose for example you just consider this solid membrane, and through this something is passing in the form of a liquid, so its diffusivity will be less as compared to the gas. So gases diffusivities are higher. So diffusivities of solutes in the solid are a few order of the magnitude less than diffusivities in the liquid. For example, we are considering any solute. Let's consider that like you have a sugar. So sugar crystal you dissolve somewhere. So solutes in the solids. For example, you want to separate those through the solids. You pass through this solid membrane, so their diffusivities are less as compared to diffusivities of the liquid. By the way, one of the student has asked me a question that sir, I always you discussed that something permeate is our desired product and retentate is just rejected stuff. So is there any case in which you can have retentate as your desired product and permeate is your undesired product? So that's possible. This will depend on the application where you are applying. This one example here you can consider, for example there were salts inside the liquid and you want to separate those salts and liquid and you are using membrane. So as you can see here that diffusivity of the liquid through membrane is easy or more as compared to the diffusivity of this solid, and then there is something liquid and solid. So you can see that gases can diffuse easily through some stuff as compared to this liquid. So based on all these things, we have to design our membrane system that we can get easy separation, and anything which can easily pass through the membrane, that is just leaving as a permeate, and other which is left over is retentate. So that can be like, it is not necessary that permeate is your desired product. Sometimes your that can be desired product, that is something called retentate. So this difference between diffusivities in gases and solids are enormous, and they affect through solids and gases if you compare. So they are large. For example, here we consider one example of water. Suppose water is diffused through some solid, some liquid, and some gas. This is one component. We are considering water at 1 atm and 25 degrees C, and its diffusivity, if we look at in these units. So just look at this: water vapor in air. Suppose water that's in the form of vapor, and that is diffusing through the air. So its value is given here 0.25. and if you consider these water vapors, and they are just passing through this ethanol liquid. So you see, this was gas, through diffusion through gas. So next, diffusion through the liquid. So that same component, same species, but now if you look at diffusion through that liquid, so its value has decreased. And if you look at this dissolved water in cellulose state, now it has to pass through some solid. So through some solid, its diffusivity is even less. So overall, from here you can see that some same component is passing either through gas or liquid or solid, its diffusivity is decreasing. So membranes are solid, you know that anything which is passing through these membranes, so its diffusion will be the lowest one. Now this same, if you compare this same water, if it is in the form of liquid or in the form of vapor, so this diffusivity will be different. So here, as he said, dissolved water, so it is the water as a liquid, this diffusivity is less. But if we want to just vaporize the water, like if we do in pervaporation, we vaporize some components, so actually that helps us to increase the diffusivity through the membrane. So that will be at least higher than this. So your more permeate will pass through the membrane. Another example, for example, small molecule were better than large molecule for diffusion. Also it depends on the molecule size. For as you know that most of the time membranes are the solid, so we will look, or we will compare the diffusivity through the solids or diffusivity in the solid of various molecule size. For example, from one book, Polymer Handbook, you have diffusivities of various hydrocarbons through the low density polyethylene. This membrane is made up of low density polyethylene, and at 25 degrees C you are operating it. And if you look at various chemicals, so it's their diffusion through this membrane is different. For example, here you have helium, then there is hydrogen, then there is nitrogen and propane. So overall you can look at this, that if you are increasing the size from here, hydrogen to nitrogen and then propane, you can see that they have high their diffusivity is decreasing as this molecule size is increasing. So based on this, for example, the question which I was discussing, that one student has asked, suppose now you have to separate these hydrogen, nitrogen and propane, so which membrane you will select, or which one will have high diffusivity? You know that out of all these, if you look at various membrane stuff, definitely they will follow the same trend. By the way, here this helium has one exception, although this is a molecule which is larger than hydrogen, but this has high diffusion as compared to even hydrogen. But other most of them follow this this trend, that as their size keep on increasing, their diffusion will become difficult and their diffusivity is decreased. So as I was talking about this, that for example you have to separate this mixture now, and your desired product, for example, is like propane. So what you have to do, you have to select such material which just reject propane, and allow these two to pass through. Why? Because they have good diffusivity, and among all material, propane will have low diffusivity. Most of the time its diffusivity will be low. So now our desired product is propane, and we are not allowing propane to pass through this membrane. We are just stopping it, because that's retentate, and that's our desired product. Because if we apply or we bring any other membrane which allow propane easily to pass through, definitely at the same time hydrogen and nitrogen will also slip through that membrane, because they will have even also good diffusivities through the membrane. So it all depends on your application and the systems and the components which you have, which you are separating. So which type of membrane you have to select, and either retentate or other permeate is your desired product. So again, also related to this topic, your book has discussed various topics and lot of equation related to the passage of gas, passage of liquid through the membranes, non-porous membrane, and then there are something called cascades of membrane are discussed. So I just skip all that stuff, just go through this half page related to non-porous membrane, and then by next lecture we will start with the next application of the membrane. We don't have to study all those equation and that stuff related to mass transfer in detail. So up to here we have discussed today some basic terminologies, or revised those, like diffusion, osmosis, what is osmotic pressure, so how osmotic pressure is important, what is the major equation or general equation which accommodates a lot of parameters for membrane separation, so that's the flux equation, and how flux is affected due to applied pressure across the membrane or transmembrane pressure, as well as osmotic pressure due to the membrane material, and also due to formation of gel or the cake on the surface of membrane, how flux is effective. We have discussed in that in detail, and then at the end we have gone through some mass transfer through the membranes. We have seen that mass transfer through the porous membranes takes place through the pores, and that's size exclusion process. Other is through dense membrane, that's diffusion through the membrane. And in most of the application, like in reverse osmosis, gas permeation and pervaporation, we have looked at dense membrane will be used. So through dense membrane, actually diffusivity of various components is different. So as membrane are the solid material, and through these membrane gases can definitely easily diffuse through, while liquid it will be difficult for the liquid to pass through, as we have seen with the example of the water. While other if even we are looking at the gases, so if you keep on increasing the molecule size, so diffusivity keep on decreasing. So keeping all these points in the mind, definitely then you design your, or you select your membrane material, and also select that either permeate or retentate will be your desired product. Thank you so much.